Water is a super cool thing. Because of water, we get to experience things like paddleboarding, canoeing, and swimming. We have access to boats, a vital form of transportation. There are so many chemical processes and organisms that need water, and drinking water is one of the many things necessary for our survival. In fact, did you know that only 2.5% of the water on Earth is drinkable? That's like a really small amount. And in the US, we use about 346 billion gallons of water per day. So we need a lot of clean water, yet the Earth doesn't have a lot of clean water. And with climate change taking away a portion of that clean water, we need to make sure the water that is clean stays clean. I'm Annika, a second-year student studying creative technology and design at CU Boulder. While I'm out here floating around, let's take a dive into the wide world of water chemistry. About 80% of the Earth's surface is covered in water. However, a lot of that is ocean water, which is salt water. We can't drink salt water. Instead, our drinking water is found liquidized in freshwater rivers and lakes, frozen in glaciers and in snow on mountains, and within soil and rock underground, which we call groundwater. But that's not all. Through the water cycle, the saltwater filling our oceans can actually become drinkable. You see, water here on Earth is constantly moving around in what we call the water cycle. Water that's on the Earth's surface warms up and evaporates, escaping up into the atmosphere as a gas we call water vapor. Then, in the sky, the water vapor condenses into clouds, which sometimes float away from the ocean and over land. Once enough water vapor has condensed, the water will precipitate as either rain or snow and fall back down to the ground, where it either freezes as snow, flows into a nearby body of water, or soaks into the ground. Then, once it's on the surface again, it evaporates and the cycle repeats. When salt water evaporates, the salts and minerals that make the water undrinkable are actually left behind. Thus, when that water falls as rain or snow, it's clean water. Well, it's not totally clean water. The water cycle does a great job of getting rid of certain things in water, but it doesn't get rid of every bad thing that could make its way into water. Before we look into how engineers turn dirty water into drinkable water, let's first look at how water becomes dirty in the first place. Sometimes our drinking water gets contaminated. Contamination is when there is a minor presence of something somewhere it shouldn't be. So, if you had some water and a drop of food dye were to fall in that water, you could say that the water is contaminated by the food dye. A lot of sources of contamination in our drinking water are actually human-made. As a population grows, so does demand for things that make our lives better but are possible contaminants, and thus we end up with more contamination. Sewage spills are a big cause of contamination. When sewage systems leak, it can cause raw sewage to end up in our water sources. In some developing countries, sewage is dumped directly into water sources, contaminating the water. Underground storage tanks can also leak and cause contamination. Have you ever seen a truck filling up the underground tanks at a gas station? Those underground tanks can get old and start to leak, leaching the gas and chemicals through the ground and into groundwater. Agricultural chemicals like herbicides and pesticides can also cause contamination. If it rains too soon after spraying on these chemicals, the rain can carry the chemicals into bodies of water and groundwater. Industrial waste spills are also a contaminant. If industrial waste is put in the wrong place, either stored deep underground too close to a groundwater source, or somewhere that it can flow into a body of water, it can contaminate water. And that's just a few examples of contaminants. So there's a lot that can contaminate water. But I do have some good news for you. Engineers have come up with lots of ways to get these contaminants out of our water. If we want to drink water that has been contaminated, that water first has to be purified. Purification means to make something pure or to cleanse something. The original way we would purify water before drinking it was by boiling it. Boiling water gets rid of a lot of bacteria and viruses, but it doesn't get rid of a lot of the human-made contaminants we need to deal with today. One of the things we do to purify water today is filter it. There are lots of kinds of filters that get different contaminants out of water. For example, our groundwater naturally goes through sand filtration when sinking into the earth, where the water slowly descends through sand, and the sand catches solid particles of algae, dirt particles, and salts that don't dissolve in water. Another commonly used kind of filter is activated carbon. Adsorption is the binding of atoms, ions, or molecules from a gas, liquid, or dissolved substance to a surface. Instead of absorbing the contaminants, like a sponge absorbs water, activated carbon instead adsorbs contaminants, making the contaminants stick to its surface, both on the outside of the carbon and within its pores. Full filtration systems will usually use several layers of filters made of different materials in order to get as many contaminants out as possible. There's also a purification process called reverse osmosis, where water is sent through a series of membranes and pumps. These membranes are a lot like filters, where they allow the water to pass through, but not contaminants. So, engineers have found ways of taking contaminated water and making it okay to drink. But what if we wanted to fix contamination in a larger context? Like we wanted to fix a whole lake, like this one? Well, that's where water remediation comes in. Remediation means to fix something that has gone bad or defective. When we have a source of water in the environment and we want to fix it while leaving it in the environment, that's where remediation comes in. One of the ways we remediate groundwater is with a pump and treat system. Basically, we pump out contaminated groundwater, treat it in a treatment facility, and then pump it back into the environment, either back underground or into a nearby body of water. We also use permeable reactive barriers to purify underground water sources. This is a similar process to reverse osmosis, but rather than bringing the water to a system with membranes, we put a giant barrier that's like a membrane into an underground water source. The barrier lets the water through, but not the contaminants, resulting in clean water on the other side. The final process we'll look at today for water remediation is nanoparticle injection, where we release a bunch of nanoparticles of iron into contaminated groundwater. Have you ever seen rust? Rust is the result of a chemical reaction between the surface of iron, oxygen, and water. Nanoparticle injection uses the idea of rust, but almost reverses it. Because the iron nanoparticles are so small, rust can't actually form on their surfaces. Instead, the iron reacts with contaminated groundwater and breaks down the contaminants into smaller, less harmful contaminants. This is still a pretty new process, though, and engineers still have some problems to solve before it can be used on a larger scale. Water is a vital part of our world, but our water can also get contaminated easily. Engineers have found lots of ways to purify and remediate water in order to ensure that we have access to clean water. And now you know the basics about water chemistry. Check out the full lesson on TeachEngineering, then use what you learned in the associated activities, chromatography lab, water remediation lab, and red cabbage chemistry.